Good day and welcome back to the fourth part of our discussion on triple integrals. In the previous few videos, we introduced the idea of setting up a triple integral over a solid of integration E, which is not a three-dimensional rectangle or a box. And we saw we had these kind of type A, B, or C solids of integration. And as we mentioned, it's not important to be able to name or distinguish between these solids. It's really just the thought process that we developed. And recall, we have this basic template we start with. We have an outside double integral and an inside single integral. And the question we want to ask ourselves for the solid E, in which direction is it varying? And here I'm viewing this solid E as varying between two surfaces in the y direction. You go from a smaller surface, U1, up to this bigger surface, U2. And that gives us our limits of integration. We go from U1 of xz in the y direction to U2 of xz. So let's go ahead and investigate an example. So let's use this idea to evaluate the triple integral of the function y over the solid E, which is bounded by the surfaces y equals 4x squared plus 4z squared and y equals 4. And the first step, as we've mentioned several times now, is going to involve sketching this solid of integration E. So if we think of a few words that might describe our surfaces, y equals 4 is maybe the easier one. That's a plane parallel to the xz coordinate plane, hitting that y-axis at 4. The first one would be a surface which is a paraboloid. Let's go ahead and sketch them. So in terms of the paraboloid, which might be the easier starting point, we have a paraboloid opening in the positive y direction with a vertex sitting at the origin. So roughly speaking, something of the form seen here, which is a paraboloid wrapping around that positive y-axis. And note, we are bounded by the paraboloid, which we've sketched, and the plane y equals 4. And note the y equals 4 is going to cap our solid off in that larger y direction. And I'm going to assume, for simplicity, that 4 corresponds to where I've drawn the circle to provide depth. And I'll go ahead and erase a few extraneous portions so that we can more precisely see our solid of integration E. So E is going to be the solid of integration going from this paraboloid up to the plane y equals 4. And I'll go ahead and shade that plane in so we can more clearly see y equals 4 versus the paraboloid y equals 4x squared plus 4z squared. And our task is to now take our triple integral over this solid E and rewrite it so that we have an iterated integral. And remember, our thought process is we always approach this from a similar perspective. We have an outside double integral and we have an inside single integral. And because we're visualizing this solid as varying in the y direction, we're going to put y as our inside variable of integration. And in that direction, we've seen that we are varying from the smaller surface, given by the paraboloid, up to the larger surface, given by the plane. In terms of D, what we have to visualize is taking our solid and compacting it down into that xz plane. And roughly speaking, if we attempt to sketch something, when this is compacted down into the xz plane, what you're going to get for D is a circular region that corresponds to this circular end cap bounding our solid E in the positive y direction. In order to maybe determine precisely what this circle is bounding our region, we need to find an intersection, which is a familiar problem. That is, I want to know where does the paraboloid intersect the plane. So we set the two surfaces equal, and note if you cancel off a 4 from each and every term, we have x squared plus z squared is equal to 1. So with this in mind, we can see our points of intersection on the positive x-axis and the positive z-axis will be 1, and our region D sitting in the xz plane is going to be a disk bounded on the outside by a circle of radius 1. And I'm going to evaluate this integral slightly differently than we have done previously. I do not need to add the limits of integration in for D before evaluating this inside integral. I most certainly have the ability to first evaluate this inside integral and see what I get back. So I'm going to start off by doing that, and in a moment I think you'll see why. So if we anti-differentiate on the inside with respect to y, we have 1/2 y squared, and we're evaluating from 4x squared plus 4z squared up to 4. And I'm going to go ahead and pull the constant 1/2 out of the double integral, which we can always do. And then I'm going to replace that remaining y squared with a 4, so that would be 16. And I'm going to subtract away from that what I get when I substitute in this quantity 4 times x squared plus z squared. When we hit that with a square, we'd be subtracting away 16 times x squared plus z squared. And if we go ahead and simplify this one more time, just to make it as easy as possible to work with, we can pull a 16 out front as well, and 16 divided by 2 would give us an 8. So we have the double integral over D of 1 minus the quantity x squared plus z squared. And this is the point where it's a somewhat familiar problem. We have a double integral that we would like to evaluate over this nice circular symmetric region D. How would you recommend we take care of evaluating this double integral? And if you said polar coordinates, I agree. Now, note there might be a bit of confusion. We've already always used polar coordinates in terms of x and y, but it's not important what variable represents the horizontal and vertical axes. It's just a matter of what we set things equal to. So whatever is representing the horizontal axes, we would call that r cosine theta. Whichever variable is representing the vertical axes, we refer to that as being r sine theta. So that x squared plus z squared is equal to r squared. And in polar coordinates, we can describe this region D as the r values varying from 0 to 1, and the theta values varying from 0 to 2 pi. So this will become 8, and now putting into polar coordinates, the x squared plus z squared is r squared, so we'll have 1 minus r squared, and in polar coordinates, the dA is r dr d theta. R on the inside varies from 0 to 1, theta on the outside varies from 0 to 2 pi. And this is the reason I went ahead and evaluated the inside integral first, was that once it's fully simplified, we see very clearly how convenient it is to apply polar coordinates, which will definitely be a technique that we frequently will use. And I just realized that you were probably yelling at me for the last few minutes. I forgot the square to go with that x squared plus z squared term. So I apologize. We need a square, and note that makes our r into a fourth power. Alright, so evaluating this integral, note it's really the ideal scenario. We can break it up into two single integrals multiplied together. And when we go ahead and distribute the r through, we would have r minus r to the fifth dr. The value of the first definite integral is 2 pi. Anti-differentiating in the second, we would have 1/2 r squared minus 1/6 r to the 6 from r equals 0 to 1. That gives us 16 pi multiplied by the quantity we get when r is equal to 1, 1/2 minus 1/6, and we subtract away what we get when r is 0. And that leaves us with the following value, and as usual, leaving it in this form is certainly okay with me. And this completes our current video. We will have several more videos investigating additional examples just to get more practice with the visualization required to sketch a solid E and set up that corresponding triple integral. So stay tuned and take care.